matter, chemical trends, and bonding. Now, for this, you do need to know the general trends, and especially you need to know them for grade 12. You need to know them for university. And in fact, a lot of this stuff you need to carry over into university. Atomic radius, electronegativity, ionization energy, electron affinity, and finally nuclear charge are things that you want to know the trends of. Trends in nuclear charge isn't so important because it's hard to say. It's hard to speak of a trend for nuclear charge, but the first four that you see in this list, very clear trends emerge from this, and these clear trends are things we can make a huge amount of use of as we move forward in grade 12 chemistry. First of all, trends in atomic radius. Notice that as we go across a row in a periodic table, the atom gets smaller. That's the atomic radius gets smaller. And the atom gets larger as we move down a family. So as we move down a column or down a family, the atom tends to get bigger, but it tends to get smaller going across a row. You cannot, in other words, you cannot quite say that atomic radius increases with atomic number. It's not quite that clear cut because, for example, sodium is a much bigger atom than chlorine, even though they're at opposite ends of the same row of the periodic table. And argon is even smaller still. So, sodium is bigger than lithium. Potassium is bigger than sodium, and potassium is bigger than anything in the third row. So that's how you got to think about that. And what else can we say? First of all, what the heck is atomic radius anyway? How do we define it? Well, I define it as the distance from the center of the nucleus to the outermost electron shell, which would be the valence shell, and which has the greatest atomic radius of these: lithium, potassium, neon, phosphorus, aluminum, sulfur. Okay, the answer is potassium, and which has the smallest atomic radius. And that's neon. Okay, now electronegativity, probably one of the most versatile things, seems to come up an awful lot in an awful lot of places in grade 12. As we measure electronegativity going across a row, it gets markedly greater. Whereas if we go down a column, electronegativity gets less and less. Once again, just due to the atomic radius increasing. So, but what is electronegativity? Maybe you can define it. This is the tendency of an atom to attract electrons toward itself. It's affected by atomic number, that is the nuclear charge, and the atomic radius. Referring to trends on the last slide, which one of these is the most electronegative element? Rubidium, iron, aluminum, phosphorus, fluorine, and lead. Okay, the answer is fluorine. Which of these was the least electronegative in the same list? And that's rubidium. Now, ionization energy, remember this is the ability to remove an electron from an atom, from a neutral atom. So it gets more difficult to do as you go across a row, but as you go down a family, down a column, it gets easier and easier. So that's the trends in ionization energy. And let's see if we can come up with a definition of this. Ionization energy is the amount of energy required to remove 1 mole of electrons from 1 mole of a pure element and is measured in kilojoules per mole. It's also called first ionization energy. Which have the greatest ionization energies in this list? Sodium, nickel, iodine, nitrogen, helium, cesium. Okay, the answer is helium. Which have the lowest ionization energy in this list? And that answer is cesium. Electron affinity. This is the ability to add an electron to a neutral atom and the amount of energy released from that. The increasing electron affinity goes across a row, and as you go down a column, you decrease in electron affinity. And so let's define electron affinity. Okay, electron affinity is the amount of energy released when an electron is added to a neutral atom to form an anion. In effect, really, it's the opposite of ionization energy. Using the general trends in the last slide, place the following elements in order of increasing electron affinity: cobalt, cesium, chromium, carbon, copper, chlorine. Here's the list: cesium, chromium, cobalt, copper, carbon, and chlorine. So chlorine releases the most energy in the periodic table for electron affinity in this of elements in this list. That makes it exothermic. Where is the trend broken? In areas where you would expect electron affinity to be positive: noble gas, nitrogen, or where you would expect an added electrons to form pairs, as in group 1a. So group 1a is way more affine than 2a, where the added electron would have to be bumped to a higher orbitals because their valence shell is already full. That means it has to go up to 2p or something like that, 3p in the case of the third row. Nuclear charge. Now these last remarks are made by way of notes. So these are just things you should know. Electrons are arranged in energy levels called shells. And because of the fact that like charges repel, electrons in the lower energy levels repel electrons further away in the upper energy levels. This is called the shielding effect. It amounts to a partial cancellation of charges coming from the nucleus. Electrons above have no effect. That's electrons in the higher energy level than the electron you're studying have no effect on the nuclear charge that it experiences. This means that electrons in the upper levels do not experience the full effect of the charges in the nucleus that the lower energy electrons do. And that's because the lower energy electrons have less shielding. As atomic number increases, the nucleus possesses more protons, so as electrons get added to the elements in the same row of the periodic table, the nuclear charges may increase, but in much smaller increments than you would expect, with the occasional decrease at the valence shell level. So each electron in an atom would have its own effective nuclear charge, which it is experiencing. Finally, our last slide today, periodic law. State the periodic law and give examples of properties that are periodic. Now notice we've already, in this whole video, we've covered pretty much all of these periodic properties which would be part of this periodic law. And here it is. The periodic law states that the chemical and physical properties of an element is a periodic function of its atomic number. So that means that as you go across a row, you have a bunch of properties changing all the time. But as you go to the next row, you get a repetition of properties that are similar in trends. So basically, that's why we call it a periodic function, is because it repeats in cycles in a more or less of a pattern. This periodic law allows us to arrange the elements in families, as shown as columns on a periodic table. Examples of such periodic properties, we've already seen the first four: atomic radius, electronegativity, ionization energy, and electron affinity. But what we haven't seen, and what you might want to make an exercise of, is take the melting point and boiling point of the first, say, 50 elements and see if you can actually detect trends, periodic trends in things like melting point and boiling point. You might be surprised at what you might find. And that's it. That's it. So,
Class, I hope you learned something from today's lesson, and if you like it, please click the like button, and please do subscribe to our YouTube channel, Charots, and click the notification bell for you to be updated sa mga latest uploads sa atong lesson. Okay, so I'm so happy to see you again, guys. Goodbye.